So if not, then we start the second lecture. And as you remember, in the end of last lecture, we discussed energy mass scale, and I put some masses of particles and some interesting recording. So we discussed this energy mass scale, and now I want to say a few words on so-called complementary scales. Namely, the scales of distance and scales of time. So we can write the uncertainty relation as delta x times delta p. And now, since Planck constant in our units is 1, because it's just 1. This means that delta x is 1 over delta p, and therefore we can measure the distances in units of inverse energy and momentum, because momentum we also measure in the units of energy, electron volts. So I can write that the dimension of x distance is dimension 1 over p. And at the same time, I can measure energy and momentum in the units of distances in centimeters. So another useful relation which will be useful for you for solving the problems is that 1 electron volt equals 1 over 2 × 10⁻⁵ centimeters. So to say the energy scale 1 electron volt corresponds to the distance scale 2 × 10⁻⁵ centimeters. 1 GeV, another unit we introduced, which is 10⁹ of electron volts, equals correspondingly 2 × 10⁻14 centimeters. In fact, this relation between energy scale and the distances has deep physical meaning, and you will see this soon. Let me put again another scale, now distances, and indicate some important benchmark points. So the distance will increase, it's better to do this in this way. So the x increases in this way, and I will start with 10⁻²centimeters, then 10⁻⁵, 10⁻⁸, 10⁻11, 10⁻14, 10⁻17, and then after many orders, I have this Planck scale, which is 10⁻33 centimeters. So that's Planck scale. Now, atomic phenomena are somewhere here at the level of 10⁻8 centimeters. And as you remember, the Bohr radius is 0.53 10⁻8 centimeters. Another important scale is 1 over the mass of pion. And since we have this connection between energy and mass units and the distance, we can identify some space or some distance, which is inverse of the mass of the pion. And this is 10 to the minus 13 centimeters. So maybe I should move the pion. So 10 to the minus 13 centimeters. And this is mass of the pion, inverse. You see, pion or pion meson is supposed to be mediator of strong interactions. So this is the particle which exchanges, and we have some strong forces. And it's not accidentally that the radius of strong interactions is 10 to the minus 13 centimeters. You see here this physical connection, inverse of mass or mass of the mediator, and the radius of interactions. Now, inverse of mass of the proton is somewhere here. It's 1 over mass of the proton is 10 to the minus 14 centimeters. Well, actually, it's more precisely let me put more precise number, 1.4, 10 to the minus 13. This is inverse of mass of the pion. Now, radius of weak interaction is somewhere here. So, and this is given by 1 over the mass of the W boson. We will discuss this later. W bosons are mediators of weak interactions. An inverse value of 1 over m, around 10 to the minus 16 centimeters, is the radius of weak interactions. Now remember we discussed tests of point-like nature of particles, or test of compositeness. And this is tested down to 10 to the minus 18 centimeters. So here is what is LHC, Large Hadron Collider, gives for us in these tests of compositeness of quarks and leptons. So it's 10 to the minus 18. And the size of quarks should be smaller than 10 to the minus 18 centimeters. So still we may have discovered some compositeness of quarks, but at much smaller scales. By the way, it's not accidentally that 10 to the minus 13 is inverse of mass of the pion, and that gives us the sizes of nuclei, and nuclei sizes are about 1 Fermi, which is precisely 10 to the minus 13 centimeters. Now this is Bohr radius, and here we have this atomic phenomena, or optics. So optic is here. Another useful relation is that 1 over the radius of Bohr radius is 4 keVs. I just inverted this 10 to the minus 8 in the energy units. And probably you remember that 1 angstrom is 10 to the minus 8 centimeters. Questions? Now let me tell now about the time scales. And again, we can use uncertainty relation, which is now delta E times delta T is 1 in our units, which means that we can measure time in inverse energy units. or we can put here without delta. And the correspondence is the following: 1 GeV equals 1 over 0.66 10 to the minus 24 seconds. So 1 GeV corresponds to very short time, 0.66 10 to the minus 24 seconds. You will have exercises also to have kind of a better understanding and handle with these units. Let me give you some lifetimes or times which are important in particle physics, just to give you some idea where we are. I will not write here the scale axis. W boson and Z boson, which are mediators of weak interactions, have lifetimes 3 10 to the minus 25 in seconds, so very short lifetime. Now, top quark, the heaviest one, has lifetime 2 10 to the minus 25, close to this. The Higgs boson has time 1.6 10 to the minus 22 seconds. Important particle pi 0. So I told already that these pions are mediators of strong interaction. It is in the original Yukawa theory. Of course, it plays an important role. So there are 3 pions. One is neutral and 2 charged, pi plus and pi minus. And pi 0 has very short lifetime. Is 8.4 10 to the minus 17 seconds. Whereas charged pions, pi plus minus, they have much longer lifetime. It's 2.6 10 to the minus 8 seconds. It's important particles and important time scale, 10 to the minus 8 centimeters. Now, muon, this is the second heaviest lepton, has lifetime 2.2 10 to the minus 6. Now tell me, what is the age of the universe? Who knows what is the lifetime of the universe, so to say, the time from the Big Bang till now? Who knows what is this?
Around 13 billion years.
Yeah, it's in the seconds. Well, once we started to put in the seconds, yes, it will be 4 10 to the 17 seconds. This is lifetime of the universe. Now, what is lifetime of electron? How long electron lives before decay?
It's a stable particle.
Well, you know, as a physicist, we can only claim that it lives longer than something, right?
Yes.
So, any guess what is the bound, lower bound on the lifetime of electron? Well, the first guess, of course, it should live longer than the universe, right? Otherwise, all electrons would decay. But the present bound on the lifetime of electron is much, much bigger. It's bigger than 4.3 10 to the 23 years. Oh, it's years now. Let me switch to years. It's much, much longer. In the seconds, you need to multiply by 7 orders of magnitude. Now, the longest lifetimes we measured is time of decay of nuclei, specific decay, which is so-called neutrinoless double beta decay. Some nuclei can decay into 2 electrons, and another nuclei which has charge which is 2 units bigger than the initial one. And we really measured these lifetimes. And the lifetimes is in the range 10 to the 23 years. 10 to 23, 10 to 24 years. So the question is, how did we manage to measure so long times, although the lifetime of the universe is much, much shorter? So it's 1.3, 10 to the 10 years. And this is, say, 14 orders of magnitude bigger lifetime. So can you imagine how we can establish this number? Even more, we can say what is the lifetime of the proton, how big it should be, and the present bound that the lifetime of the proton is bigger than 2 10 to the 34 years. So this is the present bound on the lifetime of proton. Well, we guess that it's a stable particle. But if baryon number is violated, then it decays. And this is one of the important searches these days, to search for proton decay. And we have this lower bound on the lifetime. So lifetime should be bigger than this. So how we can establish this? Any idea? Well, meanwhile, let me ask still other people to switch on video, because I see just part of the. So good, nice. So the question is how we can establish so stringent lower bound on the lifetimes, in particular proton, which is many orders of magnitude bigger than the lifetime of the universe. So this is in the seconds, and this is something like 1.3, 1.4, 10 to the 10 years. Okay, I should switch this to. So it's 24 orders of magnitude bigger than the age of the universe. Okay, so we will discuss this in the end of the course. I will discuss these symmetries and quantum numbers. And the point is that we should observe many protons. If we just have one proton, of course it has probability to decay immediately now, but in average, and decay is quantum process, so it will decay during this 10 to the 34 or 10 to the 35 years. So, however, if we have many protons, we have big amount of material and observe, then the probability that one of these protons, and of course we can take, say, 10 to the 26 and 10 to the 30 protons and observe. This is what Super Kamiokande is doing. This is a Japanese experiment. Then the chance that at least one of these protons decay during observation time becomes significant. And so this is how we establish this strong bound. Well, I should say that scales of in physics are extremely important. So the scales encode very important information. some of this information we decoded, we know what is the meaning, some not, and still we don't understand why such scales exist. And in fact, knowledge of scales already allows to make many important conclusions. So let me say a few words about the scales and physics. As I said, they encode important information, and in fact, they pose also one of the key problems in particle physics, because it's really crucial issue to understand existence of scales, and especially if you have big difference of the scales, this compose so-called hierarchy problem, and you will meet this many times. So we usually, when we construct the theory, it doesn't like existence of big scale difference of the scales due to radiative corrections and things like that. It tends to kind of to make the scales closer. And therefore, existence of scales with very big difference is actually the problem. Now, let me give you some examples where just knowledge of the scales is extremely important. So we have decays of the particle. Suppose we have X particle, and it decays into something, into lighter particles. So the question is, why it decays only into light particles? I know that many times people do this mistake. So suppose I have this X, which is at very high energies. Can it decay into particles with energy which is smaller than X, or smaller than energy of the X particle? Why a given particle can decay only into particles which are lighter than X? So for instance, we are saying, okay, neutron decays into lighter particles. Why proton cannot decay into neutron, electron, and neutrino? Of course, because the mass of the proton is smaller than the mass of the neutron. But the question is, suppose I will accelerate proton. Can accelerated proton decay? Because it will have higher energy. Do you understand the question?
Yes, but I think the answer is because we need not conservation of energy, we need conservation of the form momentum.
We need the conservation of what?
The form momentum.
Yes.
So it's a mass, not the energy. So we need less mass than the. So we can obtain. No, we need lighter particles to obtain a bigger particle.
So let me just more specify more. So we have mass of the proton, which is bigger, which is smaller than the mass of the neutron. So my question is that can proton decay into neutron plus some other light particles? You are saying, okay, you see, this mass is smaller than the mass of the neutron. But if I accelerate proton, if I have proton accelerated, can it decay still in this way? Well, the simplest answer is that decay is kind of Lorentz invariant process in the sense that if it exists in one Lorentz frame, then it should exist in another Lorentz frame. And then I always can go in the rest frame of the proton. Because if it decays, in the, say, moving frame, that it should decay in the rest frame, right? And therefore, if I go to the rest frame of the proton, then obviously, this is at rest. I cannot satisfy energy conservation, right? Because initial state will have smaller energy than the final state particles. Of course, you can do the same in any frame, but you are right, then one needs to consider not only energy conservation, but also for momentum conservation, and then one can convince yourself that the heaviest light particles cannot decay into heavy particles. Please remember this, because I may ask, for instance, during the exam, so can this particle decay into some other particles? And you immediately need to check what is the mass of this one and the final state particles. Now another question is the following. So if we have some particle which can decay into lighter particles, it always decays. One can argue that this is kind of entropy increase, because you have a given particle, you have potential energy. And then if it decays, you will have final state particles which are moving. So in this sense, you increase entropy. And therefore, everything which can decay will decay. Now, if you see some particle, X, which in principle can decay into lighter particles, say Y1, Y2, etc., but it doesn't decay, then it should be a very serious reason why decay doesn't occur. And usually this testifies for existence of certain symmetry and conservation number. So if you see that some particle cannot decay, in principle, kinematically can decay, but it doesn't, this means that it should be some good reason for this. Let me give you some examples. Kinematically, electron can decay into photon and neutrino. These are light particles. But we do not observe this decay yet. And what is behind this? Conservation of electric charge, right? Now, neutrino, in principle, can decay into two gammas. Why it doesn't decay? Because we cannot satisfy angular momentum conservation, because of spin is semi-integer, and we will discuss this, and this system has integer spins, so we cannot satisfy angular momentum conservation. There are more subtle examples, like pi meson. Remember in the table of charge pi meson, pi plus or pi minus, that has very long decay time, 10 to the minus 6. This is long in the particle physics scales. It is much longer than pi zero decay. So why it happens so? And the point is that these pines are the lightest particles which have strong interactions. And therefore, it only can decay into particles which have no strong interactions. And therefore, decay occurs, and we will see this later, due to weak interactions, which are weak, and therefore lifetime becomes bigger. Now you will have some kinematical exercises. Suppose you want to produce particle of the mass m. To produce particle of the mass m, you can collide some other particles, and the total energy in the centrum of mass of these colliding particles should be bigger than m. And so if you have two particles, if you collide, for instance, two protons, like at LHC, then this invariant mass is P1 plus P2, and these are four momenta squared. And this is what we call S. And this is amount of energy should be bigger than the mass of the particle, taking square root of this. So we will discuss this later. Now, questions? So now I'm starting the first part of the course because we had some overview and general consideration. The fixed framework will work. Now we will discuss in details many issues which I have mentioned. So the first part is hadrons and leptons, or leptons and hadrons. And I will discuss discoveries, major discoveries in the field. And I will introduce important concepts in particle physics. I have another question for you. Remember last lecture we defined elementary particle as some quantum object which is characterized by the set of parameters. Electric charge, color, isospin, etc. The important question is, can we find some alternative description, or this is unique? So to understand this, you really need to see how these quantum numbers were introduced and why, to convince yourself that this is kind of almost unique description of the particles. So it's not accidental that we introduced this set of parameters. We can try with some others, but you will fail in most of the cases. So my goal is to explain to you how do we see observed particles. How do we obtain information? So to say, why we introduce these quantum numbers and not others to describe behavior? And then I will explain what is the meaning of characteristics we introduce, and also discuss what is the motivation, which is always important. I was always curious why people did these experiments or that one experiment, and how really things develop. So one or two important remarks. One, of course, we do not see particles immediately. What we see is, so let me mark. So we do not see particles immediately. So what we see are secondary processes. In most of the cases, there are macroscopic processes, which you really can see by eye or by some trivial devices. So we see secondary processes produced by elementary particles. And so again, in the most of the cases, there are classical processes and macroscopic size processes. Second one, we still can extract information and get detailed information because we are doing experiments, and doing experiments we can still manipulate by particles. So an experiment So to say, we can impose electric field or magnetic field and to see how our observations change with this. Or we can put some screen or some piece of matter and to see how particle penetrate through this material. And again, observing effects of this absorption, we can guess about properties of the particles. So although, again, we do not see the particles themselves, but just observing secondary effects and manipulating with particles, we can really get a detailed information about the properties of the particles. So this is how we are doing the things. And usually the way we are proceeding is the following. We perform some experiment, we have some observations, and then we do interpretation of these observations. We develop kind of formalism, and then using this formalism, we make further predictions. So this is the way we actually proceed studying elementary particles. What will be in this first part of this course is that I will describe kind of selectively some discoveries of the particles to illustrate what I just presented here, the most important discoveries. Of course, I have no time to have a complete covering of elementary particles and their properties. Questions? Again, since many of you had the courses on nuclear physics, or some of you had courses on particle physics, you probably already know these things which I will discuss. However, I want to have kind of conclusions which are important for this, my description of the properties of the particles. And let me start with discovery of electron, because this is kind of very interesting and important story. And this is essentially the first particle which has been discovered. And it was discovered in 1897, 123 years ago, by G.G. Thomson in Cambridge, in Cavendish laboratory. And the experiment was the following. So let me start with the experiment. Thomson has studied electric discharges in rarefied gases. And what he saw so-called cathode rays, and he studied deflection of these cathode rays in the electric field. Schematically, the experiment looked like follows. So there is this cathode. And I will show at some point the slides with all these pictures of the experiments. And anode, positively charged, this is negatively charged, and there is some tension here. And from the surface of cathode, there's emission of something. Something which propagates. Then Thomson put the battery here. With electric field. And then he had the screen. I always kind of wondering how how this beautiful theory which we have now emerged from kind of, I would say, not very clean observations and some vague stuff, etc. But in the end of the day, we really have something which is very beautiful. So he had a screen which is made of titanium sulfide, and this material was used very often in the early days, in early discoveries. And the property of this screen is that if something hits, some rays hit the screen, there are shining spots appear, so glow. So if you have just a single particle, that would produce just temporary glow. But if you have the flux, you will have some shining spot. And in this experiment, the detector was the eye, so he was just looking at this screen made of titanium sulfide and observed the spots. Now, when he applied the electric tension, then this spot moved. So if there is no electric tension, you will see spot here. If you apply the electric tension, then spot moves, and for instance, is in this place. And so this is the parameter which we call deflection. And Thomson has studied deflection dependence on the strength of electric field. This is the basis of observations. So what is interesting? What is interesting? He actually didn't know what is the mechanism of this appearance of these spots. Now we know what is really the mechanism. He didn't know precisely how these rays, which is called cathode rays, emerged. And nevertheless, he made important discovery. So you see, it's like if you have some darkness and then you eliminate by your knowledge some small spot, although you don't know what is around. So now we know that there is excitation of these molecules of titanium sulfide, which then re-emit the photons. Now we know detailed mechanism of how it occurred, but that time it was just empirical. So there were these observations, as well as it was kind of empirical fact that something emitted. If you have some cathode and apply high enough tension, that something is emitted. So the observation were these observations of glow or some shining spot which moves when you apply electric tension. Now, what is interpretation? And actually, this story appears in many experiments. So this is how it works. We have some observations, and then we make interpretation of these observations. The interpretation was the following. Actually, it was proposed even before G.G. Thomson by Crocus. Who was saying in 1879 that actually these cathode rays are fluxes of particles, fluxes of charged particles. So cathode rays are fluxes of particles emitted from cathode with definite mass and electric charge. This is, of course, a very simple example, but you learn a lot from just analyzing how these things were discovered. So interpretation includes some hypotheses. We assume, and actually in more complicated experiments, usually there are many possible explanations. People start with various interpretations, many different interpretations, and then further analysis, more complicated analysis, allows you to select the correct one. Now, in this case, it was very simple. It was just this one hypothesis, that this is actually the flux of charged particles. Now, small theory, right? So it's kind of, again, very simple and transparent, but this is how it actually develops in many other cases. So what is the theory? If it is charged particle, that we know that there's a force produced by electric field, which is given by the charge of this particle and the strength of the electric field. Now, due to this force, there's a deviation of course, the force is in this direction, and therefore the spot or the particles are kind of deviated in this way. And the deflection is given by acceleration multiplied times square for non-relativistic case over 2. And you see, this is classical consideration, which actually works. And so the most important that d is proportional to acceleration. And this t is the time of propagation in the electric field, and you know what is this. So what is important is that d, deflection, is proportional to acceleration, and acceleration is force over the mass, and this, inserting this expression, gives us electric charge, tension over mass. Okay? So what we have found, that deflection is proportional to the ratio of E over M. Okay? So if he changed electric force strength, and he confirmed that really deflection is proportional to some quantity and the strength of electric field. And so, in this way, Thomson has confirmed the idea that cathode rays are fluxes of particles, and he measured this ratio, E over M. So he couldn't measure separately the mass and the charge, so he measured this ratio. And so later, Millikan, who actually established what is electric charge by studying motion of charged droplets of oil. Probably those who were studying this know this story. So Millikan in 1911 measured what is E. He actually measured what is the minimal electric charge. So he had these droplets which are charged by irradiation, by gamma rays, and observed the motion. And then he established that the motion is actually, can be described that there is a minimal charge. So different droplets were differently charged, but he established that everything is proportional to some certain amount, which is kind of minimal charge. And once you know what is charge, you can find what is the mass of the electron. So that was a great discovery, a great progress in the field. Now let me kind of make a resume. It's very interesting from all these stories, which probably you know. So what is called, let me make a resume from this discovery. The first is that the effect of elementary particle has been observed by eye. Actually, eye was the detector. As human eye, you see effect of elementary particle. Then you can wonder, how come that this small object, small quantum object, can produce effect which you can see by eye? And the point is because we have big flux of these particles. So from cathode, there's emission of flux, and there are billions of these electrons which hit and produce this glow. And this Y effect is visible. Okay? But what is important, the behavior of the flux is determined by effect of electric field onto individual electron. So all the electrons in the flux actually suffer from the same force, and therefore all they follow the same trajectory. And so although we have the flux, a big number of electrons, but behavior of this flux is actually determined by the properties of individual components of the flux. And this is how we see this effect. So what is important, we have a large effect, observable effect, because big flux of electrons. We would not see effect of a single electron by eye. Actually, one can see, and we will discuss a bit later, effect of heavy particles like alpha particles. If a single particle hit the screen, then you see effect even the single particle. So what I said, that all electrons have the same behavior, which is the flux is determined by behavior of a single electron. By behavior of a single electron. Single electron. And therefore we can extract information about the single electron observing behavior of the flux. So here is a mixture of quantum and classical effects, because action of electric field onto electron is classical effect. We have classical field, which actually has this force, which I have written, and that force actually induces the deviation, deflection of the electron. So we're actually using here classical effect. Of course, interaction of electrons in this zinc sulfide screen is quantum phenomenon, because these electrons then excite the levels, atomic levels, and then there's emission of photons. However, by that time, that was not known, but it was just enough to see that the spot which actually moves in a certain way. So, which means that in all these observations, there are some other phenomena involved, like emission of electrons, like this interaction with zinc sulfide. And here we use kind of empirical knowledge, which allows us to really get key information of fundamental importance of about this object. So I describe this in details because you will see that things are repeating in other discoveries at more complicated levels, though. So let me say a few words about the proton, a discovery of proton. And I remind you, probably, since many of you know, what is that? Discovery of proton followed discovery of atomic nuclei, which we have a bit discussed before. And the nuclei has been discovered by Rutherford. Or let me write here, Proton. By Rutherford in 1910. And the experiment was the scattering of alpha particles. So he used polonium, which is source of alpha particles. Alpha particles hit the screen, actually gold screen, and what he observed, the scattering of alpha particles, and the screen was surrounded by, this plate was surrounded by, again, silicon sulfide screens. And so what he measured the angular distribution of events. So he had this flux of alpha particles, and different alpha particles actually deviated from this straight direction onto different angles. And what was observed is that big angles appear. So we have already discussed this, this before. Actually, in this experiment, he observed deviation by eye because alpha particle produces significant effect in this silicon sulfide screen, so that one can see by eye this effect. This allowed to measure the size of the nuclei. How it was? So the size of the atom already was known by that time, approximately. And the main idea was that actually nuclei has the size of the atom, and so electrons are moving in this kind of positively charged medium created by nuclei. In this case, with this distribution and with this size of atom, one doesn't expect so big deviation of scattering angles. What has been observed, the main observation, unexpected, that the angle of scattering was of the order 1. And as we discussed before, remember we discussed what is the effect of the scattering on the sphere. And what we have found is that it has some peak at in this angle. Angle is the biggest one is determined by the size of the sphere, and it is inversely proportional to the size of the sphere. And so delta P was big. So delta P, this is the change of momentum, is given by electric charge over the size of nuclei. And so detection of big scattering angles means that the size is very small. And what has been established, because of scattering on big angles, that the size of the core, the nuclei, should be very small. So what has been found from this, that radius of nuclei should be 1 over delta P, the biggest deviations, and that was of the order of 10 to the minus 13 centimeters, which is 5 orders of magnitude smaller than the size of the atom. So that was discovery of nuclei. And then proton was considered as a constituent of nuclei, charged constituent of nuclei. And the story was like follows. Now, proton is constituent of nuclei. And actually, it is the nuclei of the lightest element, which is hydrogen. So proton is the nuclei of hydrogen. And the mass of the proton is approximately the mass of hydrogen. That was the idea, and actually put forward by Wien early in 1898. And confirmation of this idea was done by, again, Rutherford in 1990. When he observed for the first time nuclear transmutation, so he scattered alpha particles again on nitrogen, and he saw in the final state hydrogen plus oxygen 17. And so proton was identified as a nuclei of hydrogen. So that process was called transmutation. Let me write this. Observe this transmutation of elements. So nitrogen was transformed into oxygen, and there was emission of hydrogen atom. So that is considered a discovery of the proton. Questions? Next, a little bit about photon. It's a long story. It's a long story of discovery of the photon, which passed through early ancient ideas and then Planck observation that black body radiation is actually produced by portions. And finally, the final point was by Einstein. So for photon. And Einstein said that the light, it's 1905, final point, that the light is the flux of the particles with mass 0, with energy given by Planck constant and the frequency, and with momentum, which is given by Planck constant, frequency divided by velocity of light. So this is frequency. of the light. Now let me say a few words about tests of this hypothesis. Actually, this has been done to explain properties of black body radiation. That's what Planck started with. And then it was this idea of Einstein. The first serious confirmation again was related to Einstein idea and explanation of photo effect. So Millikan has observed photo effect. So when you have surface of material and the light, which falling down on the surface of the material, it produces electrons. So that's light. And then sometimes electrons are knocked out. And the explanation is that gamma interacts with electrons in the material and then knock out the material, and you have again electron with bigger energy which can go out of the material. The final actually confirmation was by Compton. In 1923. And what he has observed the scattering of gamma rays onto electrons. So gamma, initial state, interacted with electrons and then produced again light or gammas, which moved in some other direction. And so he measured theta distribution of secondary light in this process, and scattering was on the electron. So gamma in final state has different frequency from what was before, and he measured the frequency of light in the final state as the function of scattering angle. So this is scattering angle, and he measured frequency. You know what the frequency in the initial state and what is the frequency of this radiation in the final state. The interpretation was that here we deal with scattering of gamma on electrons. And if gamma really is a particle, you can just apply energy momentum conservation, taking into account that momentum of gamma in initial state is h nu c, energy of initial state is h nu. Now, in the final state, we have p prime. This is momentum of final photon is h nu prime over c, and the energy prime is h nu, and h is Planck constant. So making this interpretation, you can really find or connect using energy momentum conservation, you can find what is this dependence. Just using usual kinematics, energy and momentum conservation, you can find what is the energy or frequency in the final state using this identification. So it should be prime. And this simple theory really confirmed what Compton has observed. So really you can treat a photon as a particle with certain momentum and certain energy. And using energy momentum conservation, you can predict this. So this is energy momentum conservation, which is used. To predict this dependence on the basis of what you actually have in the initial state. So this was final point in conclusion that we have really particle, which is that the photon is really particle. Questions? Okay. So let me discuss next discovery. And this is discovery of neutron. This discovery has also some history. And probably first step, let me write neutron. Discovery of neutron. The first step was observation by Bethe and Becker in 1930. Oh, sorry, Bethe and Becker. It was observation that alpha particles emitted by polonium, the element is very often used in this early time, acting with beryllium target, produce some new radiation. Which actually produced later some effects, but this radiation was neutral, so it was something neutral which is produced in this way, quite very penetrating. So it produced penetrating radiation alpha plus beryllium gave, and let me put the present notation N plus something. So something has been produced in interaction of alpha particles with beryllium target. So it was not affected by electric field. So that actually confirms that this is neutral. It's neutral. Next step, and it was some suspicion that maybe still it is gamma. So the main question was if maybe this is gamma. Actually, it was easy in the early time because number of particles known by that time was too little, and therefore, so you can really check if your observation coincides with what you have already discovered or not. So the first suspicion that it is photon. However, it was also observed that it is a bit stronger penetrating particle than photon. The next step was by Julia Curie and Joliot. They studied interaction of this new radiation with paraffin. So they also had this type of interactions of alpha with beryllium target, but then they put paraffin. Which is material which contains many free protons. And what they saw that this new radiation actually emits, knock out the protons from paraffin. it was already that time suspicious that maybe this is not gamma. Because what they did, they also measured the momentum or energy of this proton, and the energy or momentum was about 5 MeVs. Just using simple kinematics, one can test that to produce protons with this kinetic energy, this is kinetic energy, one needs to have gamma about 50 MeVs, which was not certainly emitted by polonium. So already was kind of question mark if it is gamma or not. And the analysis is really simple because number of known particles was too little. And you can check first to discover something new, that already known particles cannot produce the observable effect. So is this something neutral? And by that time, people knew that photon is neutral, right? So then the question is if it is gamma, if it is a photon or not, which is emitted by this interaction of alpha particles with beryllium. But again, just simple kinematics gives you that you need too high energies of these photons, which cannot show up here, to produce proton with momentum of energy, kinetic energy of 5 MeVs. And actually, the final point was done by Chadwick. And the Chadwick has the following experiment. So again, he used polonium. I have some maybe better. So his device was like that, and I will show you the real device, how it looks like. Polonium, which emits alpha particles. Polonium was somewhere here, and these alpha particles hit beryllium target. Then some radiation shows up, and then he put this paraffin. And here the protons appeared. And then he put actually small ionization chamber. So that was kind of, you see, some other step. So he put ionization chamber. So it has this kind of arrangement, and here it is connected to amplifier. So protons, which appear here, produce ionization in this chamber, and then ionization of the signal of the pulse is collected by the plane here, and it was then amplified. So he saw some signal. So whole the story is the following. That was known before Chadwick. Now, what happens here in beryllium target? Here is beryllium, right? Alpha particles. Here, beryllium target. Helium 4-2 plus beryllium 9-4. And what is produced? Is produced carbon 12-6 plus this mu radiation. So that's what happens in this. That was known. Now, this new radiation interacts with paraffin, right again. This is paraffin, and produces protons. This also was known. What actually Chadwick did is he put here this ionization chamber, and measured what is so-called range. Essentially, this is energy spectrum of these protons. So measured range, what is called. Of protons. So protons enter the chamber, they lose the energy and stop. And so he measured what is essentially distance which protons propagate here when they lost the energy. And this way they can reconstruct what is initial energy of the proton and therefore spectrum. Now simple kinematics can tell you what should be the mass of this particle, what we call neutron now, to produce a given spectrum of protons in the final state. So it was average 5 MeVs, but it was a spectrum. And therefore he knew what is the momentum of this particle. And you can use just simple kinematics to establish that the mass of this particle should be of the order of the mass of the proton. Essentially, that was discovery of the particle. What he has established that the mass of this new particle is approximately the mass of the proton. So that allows you to explain kinematics of this process and the energy of protons which are emitted, and that allows to explain what is the energy of the protons measured in this ionization chamber. So that was the final and key element of this discovery that, considering kinematics of the processes, the mass of this new particle should be of the order of the mass of the proton. And that time everything was easy because people knew just photon, right? And if you have something new which has mass which differs from mass of the proton, this is already discovery of something new, right? So that was discovery of Newton. Questions? So everything is clear? Tell me. So, okay, next lecture we will discuss discovery of neutrino. And probably I will prepare already the first set of the exercises for you. I was always amazed by the fact how our beautiful theories you have now, the standard model, emerge from all these observations. which look like, not very perfect in a sense. It's something dirty, something which is one is still convinced that everything is fine. But that's the way how the standard model was constructed. And one of the goals of my course is just to show what all these steps and elements, which actually led finally to construction of the standard model, which is our present theory of elementary particles. Okay, so if there's no question, then I will see you after tomorrow, right? Again, on the screen. Now let me still ask, is it okay? I'm usually asking, so if you have some recommendation for me, because it's difficult to have any feedback using just these screens. And usually I'm asking questions, should I move faster or slower? Skip some details, or what is your opinion? Should I have more explanations, or it's okay, or speed of the exposure of the material?
It is okay for me.
Well, what I'm doing usually, I meet every student and just discuss individually, because I understand that you came and we have different levels and different courses before us. So for some of you, maybe already well known things which I'm discussing now. For some is new, but eventually we will really break everything. So don't worry about this. Even if you just do not understand or miss something, we will try to recover all the things. But for this, I will need your feedback. I don't know how we are organized this time, but again, in the previous years, I met every student individually and asked questions about and recommendations what he considers should be done. You can send me actually an email if you want. So we are still discussing how to do things in kind of more in person than just looking at the screens. It's kind of it's difficult. We never had this experience before, so I don't know how it will work eventually. And I need to have your feedback, of course, because it's just looking at the screen. It's even more difficult to understand what is the level of how you understand things. When someone is sitting close to you, it's easy to do this, but from the screen, especially some of you are not even turn on the video, which I want to still to see your faces, and okay, maybe someone go to drink coffee already. This I don't know. Okay, so then see you after tomorrow, right? And we'll continue with neutrinos and then further discoveries. Okay.
See you. Thank you.
Thank you, Professor.
Okay.
Thank you.